Alright, this is the Helix RS. This is the Fantom. This is one of their newer versions that I have here. This is the 21.5. This motor, I got it so I could compare it in my USGT. Here at local track, we do not use the gravity spec motors. It's an open 21.5. That's the reason why I got this one. The build construction is actually very, very beautiful in this motor. I have a 17.5. It's gorgeous. I like the silver plating on everything, so everything's silver plated. And just in general, it's assembled nicely. So just out of the box, I'm going to go ahead and connect it. Now, in the past, I've put motors on the analyzer, and when I've put them on the analyzer, I've gone down to maybe 30 degrees of timing, 35. I'm not going to do that because it's somewhat pointless. One is never going to run such low timing in a competitive setting. The only reason why one may decide to run, say, 30 degrees of timing is to get over an hour runtime out of a battery, which is possible. Maybe just messing around, driving slow. There we go. Need to make sure that doesn't contact. All right, I think that's fine. But we'll see. We'll see what the timing is. Now, Fantom, one of the things that I like is they always come with these test sheets. So this is the information for this particular motor. So anytime you buy a Fantom, it comes with this, and then they will tell you what the other specs are. So strength, 1750. So supposedly this rotor is 1,750 Gauss. As of this time, I do not have equipment to test that. So I'm just going to do the timing in kVs. But let's see what the timing is out of the box. This one's actually a lot closer. So the end bell reads 50 degrees. On the 17.5, when the end bell reads 50 degrees, it was at about 5 degrees under in reality. So that's something to be mindful when you're buying motors. Not all motors are exactly the same, even from the same manufacturer. So let's go ahead and do a kV run. Now, a quick note, many times I like going to this light, then this light, and this light. That way you can see the low, mid, and high range. So you would have to pause the video. When I show you the data table, I'm only using the high end, high range. So this is about 5.1 amps. The other motor came in at 5 amps out of the box, which is fabulous. These motors come in just ready to be soldered on and run without any problems, so there's no guessing. If you want to go up timing, I would probably go maybe 1 notch, and that's as far as I would go. I don't really think there's a need. I am going to go down in timing according to the end bell 5 degrees, and then I'm going to go up 5 degrees from where it is now. So those are the two. Now, in the past, I've tested these motors at a different voltage. 7.6, for example, is a common voltage that I've used. I'm using 8.2, and the reason why is for the longest time, just based on many motors that I've run on the analyzer from other brands, as the voltage changes, so does the kV. And I know that sounds a little weird because the kV is supposed to be a constant. So in theory, it should not change because it's constant. If it changes as voltage goes up and down, then it's a variable. It depends on the voltage, which was my belief many times, and I do mention this in past videos. But on these Fantom motors, for some reason, it's the same. There's no difference. The kV may vary very, very little. And usually with the other motors, as the voltage went up, kV reading was a little lower. As voltage went down, kV reading was a little higher. The RPMs were still lower because of the voltage. But not here. Here, actually, 17.5 in this one, I'm just not going to bother including in the video. It'll make it too long. But it's the opposite. Voltage goes up, and the kV goes up, but it's not a significant amount. It's actually a very, very small amount. It's generally within 20 kVs. Let's see, so we'll do 5. Now the end bell is very, very smooth on this. So when you tighten this, you have to be careful that the end bell doesn't walk. And what I mean by that is that as you're tightening this, the end bell doesn't accidentally rotate as you apply a torque. Now, another reason why you want to tighten slowly is if you tighten one side too much, the sensor on the end bell may not seat properly. So it may actually end up being closer to one end versus the other. So it'll skew the timing. Let's look at the timing here. Not bad for a 21.5 motor. I'm going to have a data table where I compare this to some of the other tests that I have done. And I'm just going to ignore the voltage difference because this is so close in kV. As I said, it's if I test this at 8.2 versus 7.6, the kV difference is about 20. So as far as I'm concerned, it's negligible. And this has been a surprise for me, and it's been a surprise with these Fantom motors because the other motors, there's always a difference. So these motors have sort of shocked my world. All right, so now I want to go 5 higher than I was, so 50. All right, that's close enough. Now, another thing too, so if you're new to timing on motors, things like that, the reason why I grabbed the driver down here isn't just because it's more comfortable to work with the cans, but because I apply less torque naturally than grabbing it from the handle and grabbing it like this. So if I grab it this way, I just roll it on my fingers and I can feel how much torque I'm applying to these screws, because again, you do not want to over torque them. You can try it if you want. I don't recommend it. You're going to see how it affects timing and everything. Here, let's see. All right. And let's go to motor timing. All right, and the timing's pretty close. It's within 2 degrees, so that's good. I've tested some other motors that are 7 off between one phase and another. Let's see, so let's do a kV run. So I'm expecting this to pull about 6.2 amps. By 6.2, this thing's almost at 8. 17.5 did about 16.2. Sorry, 6.2, I mean not 16. So KVs, wow, they're pretty high. They're pretty high. I would not recommend you run it this high though. Once you start going above 6 amps, the motor is actually very inefficient. It's going to consume a lot of amperage, as you can see, which is the juice in the battery. So your battery is going to die a lot faster, and it's going to produce a lot more heat. So it'll be difficult to cool the motor. But that's what we have. Now I'm going to put everything on the data table, and I am going to try to put the motor in probably about 5.5. That's going to be my goal. So we'll see if I can get this at 5.5. Mainly because 21.5, I mean, they consume so little. There we go. So if I go here, so I'm trying to match a 52. Well, what I mean by that is the line, let it be at 52. That's my goal. All right, let's see where my timing is. So if I get about a 50 or a 51, I'll be happy. 50, perfect. All right, so I like that. So that's 51, 49, 49. Great. This is actually perfect. So I'm expecting this to be at about 5.5 amps, hopefully. So I'm just going to, well, I guess I'll show you the whole thing. It's actually somewhat high, so I'm probably going to end up turning it down to what it was out of the box. If it's a cool day, I would consider running it this way. If it's not a cool day, then I would not run it like this at all.
This is the data for the 21.5. So the Fantom Helix I've gone ahead and put in at the very bottom, and I'm going to be comparing it to the Trinity slot machine and the Hobbywing V10 G4. These are the only 3 motors that are worth comparing. I do have the information for the Trinity X Factor, but it's not worth comparing. You can see some of the data here, but the Trinity, the slot machine, is a better performing motor than that one. So I'm going to go ahead and ignore and just focus on these. Now, one of the things to note, I did not record this run, but I decided to mess around with the motor after I turned off the camera just a little with the end belt to try to get it as fine-tuned as possible, which is pretty much just loosening screws, tightening them, different order. It didn't take me that long, but anyway, I decided to keep these. So it's 49, 49, 50, 50, 48, 49, 48, 48. So I got these a little closer. And that small little bit, yes, the amp consumption did go up from 5.1 to 5.5. So this is out of the box. This is how the factory set it up. And this is how I set it up. Now there is a small little drop in voltage here. Something to keep in mind, but the point is kV. Well, there's a small gain, so there is a small gain. So there's something to say when the timing between the phases is as close as possible. All right. Well, I'm going to leave that there. But that's the reason why I put this in different color. This is the way I have the motor set up. This is how I'm planning on running this. But let's see. So previously, we had, let's see, Hobbywing, Trinity. I do go over some of the other specs if you watch my video on the slot machine or just the Hobbywing compared to the other motors. But like I said, I'm going to ignore it. But here we have a 4.1 versus this 4.0. And one of the things to notice is the timing is 46 on both of them. KVs are very similar. Hobbywing having the higher KV slightly. 2,591 versus the 2,510. And those are really the only ones that match. I mean, we have these here versus this. This is somewhere in the middle. So if we look at the KVs, it's still higher KV. So 5.8 amps, less amps versus the 6. Trinity slot machine is at 2,705 kV versus 2,785. So the Hobbywing generally, as far as KVs, it has higher KV. Now, as of the time of this video, I do not have a way to test the Gauss on these rotors, so I'm not sure what it is. This one here should be, I believe the Gauss on this rotor was about 1,700. Approximately 1,700 or 1,750, somewhere around there, if I recall correctly. I could be wrong. You can put it in the comments. But here's the Fantom Helix RS. So the Fantom Helix RS does come with a test sheet, and according to the test sheet, the rotor has a Gauss rating of 1,750. So that's what we are looking for in the case of the Fantom Helix. Now, KV can be affected by a variety of things. So for example, if you have the same rotor, in the past I've tested the same exact rotor on a Trinity slot machine and the X Factor, because the rotors are interchangeable. And the Trinity slot machine yielded better KV than the X Factor. So that's a can difference, which was awesome to see. So I took the same rotor and just swapped it out, which is great. Now, if you have different cans, well, it's very difficult. You really don't know, because then you introduce other variables. But if you have the same can, generally, if the diameter of the rotor is the same, so let's just say the dimensions are exactly the same, higher Gauss will generally yield less KV, lower Gauss will yield more KV. And then torque, well, it would be the opposite. But with the Trinity slot machine, I took the same rotor, just swapped the cans. This one has a far better can, in my opinion, given that result. So now, so I'm just talking about all the 20 billion variables that could be present. So the Gauss in this rotor and this rotor should be about the same. So here we have, let's see, what can we compare? So 5.5 and 5.1. So we have these right here versus this 5.3, which is 49 degrees as well. And we're looking at a 48, 50, 50. So that's going to be closer to this as far as timing, but we can compare it to both. And we're looking at 2,609 kV versus a massive difference. This is a huge difference. This is 2,849, 2,952. Even if I go with the lower one, it's, here we go. So we're comparing it to this number here. This is a huge difference. Notice that 2,697 is closer. There's still a big difference. The Fantom Helix would only be pulling 3.4 amps, which is nothing. This motor would be running as cool as could be. Runtime would be long. This would be a long runtime. So 3.4, if we went based on amps, so I would select that, and let's say we go with this 3.5. We're looking at 2,481 kV versus the 2,697. There's a gentleman that I was talking about. He was asking me about the Hobbywing V4 in the comments. I forget the video. I want to say it was the 21.5. Maybe it was the 17.5. It might have been the 17.5. But I did kind of steer him toward the Fantom. I am a fan of Fantoms. That's a disclosure. I do like their motors. I do like the quality of their motors. So that being said, slot machine is, well, lower kV. So let's look at the Hobbywing. We knew the Hobbywing was higher kV than this one. So let's try to match these up. And I really don't have anything to match up exactly. If I go with this 5.8, I'm going to have to go based on timing. So 50 degrees of timing, 50 degrees of timing down here. So we have a 50, 51, those match, 49, those match, and then 50 on the Hobbywing, 49 on the Fantom. Close. So it's close. But not so close. KV Hobbywing 2,785 versus 3,058 kV. So the Fantom does have much higher kV. It's almost 300 kV. It does draw more amps though. It's 6.3 amps versus the Hobbywing 5.8. So that could be a potential issue. But here's the thing though. If we just go down to, let's just say 5.5 amps and call this close enough. Now this one's already selected because this is how I set up the motor now. So I'm going to select this top one just so we can compare them. We have Hobbywing 50 versus 49 degrees overall. So Hobbywing phases 51 versus 50, 49, 49, those match. And then 50 versus 48. Amp drawn, Hobbywing is drawing 5.8 versus the Fantom 5.5. The KV in the Hobbywing is 2,785 versus 2,952. Almost 200 kV difference. So there's quite a difference. Now, again, I don't have information on the strength of the rotor for the Hobbywing because that could make a difference. But the slot machine and the Fantom, these have very similar strength rotors. So these, I would take them just face value. That's what I would do. The Hobbywing is a bit more of a challenge. So which one to pick between the Hobbywing and the Fantom? It's going to be up to you. Look at the data, sort of analyze it. I'd still recommend that you go back and watch these videos. And the reason why is whenever I put them on the analyzer, as you noticed, I will go partial throttle, higher on the throttle, and then full throttle on the analyzer. So you can also see the low and the mid range between them, because that could also make a difference between whether you want this one, or this one, given the type of track, size of the track, and the surface of the track. So don't just go based on this and then say, oh, Fantom's the latest and the greatest. Let's all buy those. I mean, if you do, then, welcome to the club. But, keep in mind, every motor is going to have a different quality here. So I don't want to steer you one way or the other, but these are the numbers that I got out of my test. So before I ran both motors in my USGT car, so this is the Trinity slot machine. It's 2,704 kV. The battery voltage is the same, but it is running at 6 amps. Now, both of these were at the same timing. It was 50 degrees timing. If I wanted to, I could have put up the timing a little higher on the Fantom. But these higher turn motors are very sensitive to change in timing. So really, it would have only been maybe 2 degrees more. But you can see the kV is 2,940, so significantly higher. Voltage is the same, but it's 5.5 amps, and which is why I mentioned that I could have gone 1 or 2 degrees higher just to match that 6 amp. So this isn't exactly apples to apples, but it's close enough. So using my SkyRC GPS GSM 020, that's the one I generally use for my drag car, I went ahead and just did 3 test runs each, just to see what it would give me as far as acceleration and speed. So here's the data. The general data. So on the left side, I have the Trinity slot machine information from the test run. So I took the same car and just ran them. So I put my GPS on there. This is the one I use for the drag car. And I purposely highlighted second 1, second 2, because the way the GPS works is, as far as satellites, it measures every second. And then internally, it has something that measures force, so that's how it estimates or calculates the rest of the speed. So really, it would measure at second 1, well, I guess 0, then 1, 0, 0, then just 1, 2, and then 3. That's the reason why. That's how those work. That's from SkyRC. Let's see. So the model would be the GSM 020. But here we go. So this is run 1, 2, and 3, and this one was super fast. I was actually surprised. So I'm not sure if this is a fluke or not, but I included it because I did 3 runs, and then I did 3 runs over here, and this was actually the slowest for the Fantom. But if we look at the very first run, so at 1 second we're looking at 35.5, say 36 kilometers per hour. Second 2, we're looking at 59.5, let's say 60 kilometers per hour. Top speed overall, 63 kilometers per hour. Those are the G's of acceleration compared to G's of acceleration over here, and then 64 peak. Now, second 1, 45 versus the 35 or 36, 62 versus the 60. So that's the difference in the acceleration right here. But don't get too excited because this one slowed down, this one did not. Well, according to this. Now we have 1.35 Gs, 1.31. So these Gs are now closer, a lot closer Gs yet. Top speed 63, 64. But we're going to ignore the top speed. We're just going to look at 1 and 2. So after second 1, 38.5, say 39, 44.5. That was very interesting. Why? Because the peak acceleration, according to this, was at second 1. Before that, it was actually pretty slow on the takeoff. This was faster on the takeoff. Second 2, we have a 60.5 versus a 60. So this one's actually faster at this point. But top speed, this one reached 64, this one 63. So it's interesting. I mean, take this data with a grain of salt. The best way to do this test, to be honest, would be to take it to the track, put one motor on, get a few laps in, and then take, say, your top 10 laps, and then swap the motors, and then take your top 10 laps and see how you do. But here we go. So this one, as you can see, and no, I didn't confuse the data. This does belong to the Trinity. So we went from a consistent 325 to a 315. This one could have been a fluke, maybe, but I still included this one. 1.52 Gs. Now, what could have caused this? I don't know. Maybe the sensor was just aligned better during this run compared to this one. That's a possibility. When I first ran this one, to give you an example, I accidentally forgot to connect the sensor cable, and it was a 3.8. So that's how much difference the sensor cable did, just because of the timing. It was cogging in the beginning. So that could be why this one is faster, and that could be why this one is slower. Just the way the motor happened to be aligned at the start. That will make a difference. But let's look at 1. So 1, we have a 43.5 versus a 34. This is a significant difference. 2, 61.5 versus a 57.5. Not that much difference, but it's interesting that the top speed is 64 and 64, so they still managed to get to 64 and 64. And if I were to compare this to one of these other runs, see how it says 3.2? So if I now compare the fastest for the Trinity versus the other ones, the Trinity is still pulling faster numbers at second 1. So that's a 44.5. Sorry, the Fantom. I apologize. The Fantom is still pulling faster numbers. So even though it's a 3.2, this is a 44.5 versus a 33.5. Okay, this one's slower. This is 60 versus 61.5. Let's look at the top, 45 and 62, even though it's a 3.2 versus these numbers over here. So It just depends. If we were to ignore the very last run for both of them, it almost seems as if Fantom had a slight edge over them. But I am not willing to claim that simply because of these. See, this one looks realistic. This one, not sure what happened. Like I said, it could be the sensors. So if I only did 3 runs. If I'd done 10, maybe I could have found a pattern or been able to toss one. But as far as this table, like I said, take this data with a grain of salt. The best way would be to take them out to the track and then try them out, actually race them. But for now, thank you very much for watching. I hope this was useful and informative, or at least entertaining. Please subscribe if you have not, and I'll catch you on the next one.
What? Oh, my hair! My tongue! My rod!